Today, in this video lecture, we will see this concept conditions for no tension. So, first understand this figure that this is rectangular column fixed at its bottom and A and B points are there. See this A is this edge and B is this edge, and on that column there is eccentric load is acting this. So due to that eccentric load, and this eccentricity is at a distance E from its centroid, and this is axial load. So what will happen due to this load? This column here moment generates, and due to that moment this column tilts like that. Why this will tilt like that? Because there is reason. And what is this reason? See, here at A compression forces comes, and here at B tensile forces comes. So that tensile forces are the reason of that tilting of column. So in another wording, that means these tensile forces are not good for that column. So that's why we are deriving that condition for no tension condition. So, and we all learn that maximum stress is equal to direct stress plus bending stress, and minimum stress is equal to direct stress per minus bending stress. So I will tell you that sigma minimum is equal to that direct stress is nothing but the P by A, and minus bending stress is that 6 PE by AB. P is load and E is eccentricity, A is area, and B is width of that section. So from this, what is understandable is, see, this is sigma 0, this is sigma B. So what is understandable is that if sigma 0 is less than sigma B, that means if it is sigma is 5 and the sigma B is 15, what will happen? Put this in that equation. So sigma minimum is equal to 5 minus 15, that means it is minus 10. Minus, that means tensile nature. So that's why it's all is happening. So terminate that condition and apply this condition. Which condition? That sigma B should be greater than equal to sigma 0. If that sigma B is 15, sigma 0 is 5, then what will happen? Put here that 15 minus 5, it is 10. Either you can, if you will equal it, then it is only 0. So 0, that means no tension. Here no tension condition. So apply this condition and try to derive that condition for no tension. So if we apply this condition, then sigma 0, we all know that direct stress is nothing but the direct load divided by area, and sigma B here m by z. How sigma B comes? See, bending formula, we all know that m by I is equal to bending stress divided by y and E by R. This m is nothing but the moment. I is moment of inertia, sigma B is bending stress, y is distance between neutral axis to that elemental strip distance where we are interested for finding that stress, and E is modulus of elasticity, and R is radius. So m by I is equal to sigma B by y. So this sigma B is equal to my by I. So m, take this y in denominator, I by y, and you know that sectional modulus is nothing but a moment of inertia divided by that distance between that moment of that particular moment of inertia axis to that where we are interested, to that condition, that strip. So this y, we are talking about that y. So that way this sigma B formula derived, and this moment See here, this P is acting and this eccentricity is E. Moment is nothing but a load into perpendicular distance, and we have been taken moment here at this point, so moment is equal to P into E. So put here this moment P into E, here P into E. So this P will get cancelled. This Z take to left hand side numerator, so Z by A. So this is important, right? E should be less than equal to Z by A. So if E should be less than equal to sectional modulus divided by area ratio, then only there is no tension condition happen. So from the statement, so see, understand this statement. If area will increase, then this eccentricity will no. See, from that statement we cannot see understand. If eccentricity will increase, then what will happen? Area will decrease. Like relation, see, eccentricity and area, inverse relation, eccentricity and sectional modulus, there is directly relation. But understand that from this condition we are able to decide where we need to put that P as eccentricity. Like, okay, if we put less than this ratio, less than this sectional modulus by area ratio, then in our column will be safe. So we have that E value. Now we have judgment about that eccentricity. Like we have that control now where to put that E. Then only thereafter that no tension is happening there, and our column will be safe like that. So remember that eccentricity should be less than equal to sectional modulus divided by area of that particular column. Thank you very much. Hello, today in this video lecture we will learn that middle one-third rule. So what is that middle one-third rule? Middle one-third rule, that means here this is rectangular section. In between that middle there is no tension condition happens. So that's why this is middle one-third rule, and we will calculate that area, we will calculate that region where no tension condition is occurring. So first understand this diagram. This is rectangular section. This side is B and this depth is D and width is B. This x axis and this is y axis. So for solving that middle one-third rule, we will get help of that condition of no tension. So we learn that condition of no tension. What is that condition of no tension? E should be less than equal to sectional modulus divided by area. So with the help of that we will calculate this condition of no tension. So first, see, this is x axis, this is y axis. So consider this as the x axis, this sectional modulus as z axis, and this as area, and this as y axis, this has sectional modulus about y axis, and this has area. So let's solve this sectional modulus. You all know that sectional modulus is nothing but the moment of inertia divided by that y, and this area is as it is. Similar here moment of inertia about x axis, and here moment of inertia about y axis, this y and this a. So this moment of inertia about this x axis, that means parallel to that x side is b as it is, another side is d cube divided by 12. Now this y, so how to calculate this y? See, we are calculating moment of inertia about that x axis. So calculate this y with respect to that x axis. That means like that, from that x axis. What is that distance? This total is d. So that means this is d by 2. So d by 2 into area. Area of that rectangle is this b and this d, multiplication b into d. So here see, this is not only equal to, this is less than equal to. Similar here, I is nothing but this y axis, and parallel to that y axis is d. So d as it is b cube divided by 12, and measure that distance, y distance, to extremities from that y axis. So that means this. So this is b. This side is b. So this is b by 2. And this area is same b by d. So see this 2, here this is 6 come. Calculate it mathematically. This b get cancelled, this d, 1d get cancelled, that means here d square is remaining. D square divided by d square, that means see here is also 1d, 1d cancelled, d by 6. So ex should be less than equal to d by 6, middle one third rule. And here ey is equal to 6. This b 1b get cancelled, this b 1b get cancelled, and remaining is only 1b. This d get cancelled. So b by 6 here less than equal to. So focus on this outcome. So this ex is less than d by 6. So eccentricity should be less than d by 6, and measure this eccentricity from that x-axis with respect to that x-axis. So see, this total is d. That means here this total is d. That means here somewhere d by 6 comes. This region ex, and below also d by 6 comes ex. And now this ey is b by 6. Measure ey with respect to y axis, that means from y axis. Now see, this is b, and from y axis b by 6 is will come here, also here also b by 6. So this ex is, what is this ex? Ex is d by 6. This x is also d by 6. Then this b by 6 is nothing but that is ey. So this ex is equal to d by 6 plus d by 6. That means ex is equal to d by 3, and this ey is equal to total ey. I am talking about total ex and total ey. This total ex and this total ey. So ey is equal to b by 3. So see, make points here. See here, 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 and join that points. So see, this portion is no tension portion. That means if you put load here in that portion, then there will be no tension here. But if you will go outside that portion like here, then there will be tension come into picture. So this is middle one third rule. Remember that E should be less than equal to D by 6, E should be less than equal to B by 6, and remember that area. So that is about it. Thank you very much. Now in this video lecture we will see this middle quarter rule, and there is different name for this middle quarter rule, another name also, that core of section or kernel of section. So what is that core of section or kernel of section? So see definition of that core or kernel of section. the centrally located portion of a section within which the load must act so as to produce only compressive stress is called as core of section or kernel of section. That means that the centrally located portion of a section like that within which that only compressive stress acts. So with if we put our load here in that circle, then only compressive stress will produce. So that is meaning of that kernel of section and core of section. And this is that central region. This is in central region. The centrally located portion of a section within which the load must act so as to produce only compressive stress is called as core of a section. So within that region there is no tensile stress. Tensile stress is outside that region. Here tensile stress will come, but within that region there is no tensile stress. So see derivation of that middle quarter rule and core of a section or kernel of a section. For that middle quarter rule, this shape is circular shape and of diameter small d. This is x axis and y axis. So with the help of that our last derivation regarding eccentricity, that zero tension eccentricity, so this derivation is like E should be less than equal to Z by A. Z is sectional modulus, A is area. So see this, consider one axis xx, so Exx should be less than equal to Zxx by area. So this Zxx sectional modulus is nothing but the moment of inertia divided by y. So the moment of inertia of this circle, what is moment of inertia of circle? Pi by 64 d raised to 4. And y, we have consider moment of inertia for that xx section, so consider y from that xx axis, so like that. So dia is small d, so that means this is d by 2, so this is y. And area of circle is pi d square by 4. So rearrange it mathematically. Exx should be less than equal to pi by 64 small d raised to 4 multiply by 8 by d pi d square, d into pi into small d square. So this 8 for the 64, this d, this one d gets cancelled, this square, only d is remaining, then this pi get cancelled. So 8 is a 64, so remaining is d by 8. So see this eccentricity should be less than equal to dia of circle divided by 8. And see, you all know that moment of inertia for Ixx and moment of inertia for Iyy axis for that circular shape both are similar. So that's why, and area is similar for that, area is 1 for that circular shape. So Eyy should be less than equal to d by 8. So our objective is complete. Now see Exx, that means from xx axis. So here, somewhere here d by 8 comes, somewhere here d by 8 comes. That means from this central location towards this, like that. And Eyy, that means see here from y, here d by 8 and d by 8. So these are the points. Now join that point. This is circle, so join it as a circle. So this is core of a section or kernel of a section, this hatch portion. So in between that core of a circle or kernel of a circle, there is only compressive stress will develop. No tensile stress will develop inside that core of a circle or kernel of a section. Outside that section, tensile stress will develop, because see, whenever we apply our load here in that region, then no tensile stresses will develop. But whenever we apply our load here outside of that kernel, so there will be chances to develop that tensile stresses. So that's why this is this is d by 8 plus d by 8. That means d by 8 plus d by 8. That means 8d plus 8d, 16d divided by 64. That means d by 4. So this distance is d by 4, and this distance is also d by 4. So remember that middle quarter rule. Dia of circle is small d, and that kernel dia is d by 4. That's why this quarter word comes. Middle quarter rule. That quarter is nothing but 1 by 4 d. So thank you very much. Now we will see eccentricity for hollow circular section. So methodology is similar. See that eccentricity, that no tension equation is eccentricity should be less than equal to that z by area, sectional modulus by area. So apply that similar methodology here. Exx should be less than equal to zxx by area. I consider that xx axis. So this exx less than equal to ixx by y. How this ixx and y come? This is nothing but the zxx. Sectional modulus is nothing but the moment of inertia divided by that distance between neutral axis to that extreme fiber distance. So exx should be less than equal to ixx for hollow circular section is nothing but the pi by 64 in bracket. See, outer diameter of the circle is capital D raised to 4 minus inner diameter small d raised to 4 divided by y. So we had considered xx section. So this y is nothing but the distance between that, from that xx section to the outer fiber distance. That means this. So this dia is capital D. So this is capital D by 2y. And area is pi by 4 capital D square minus small d square. So rearrange it mathematically. Exx should be less than equal to pi by 64 d raised to 4 minus small d raised to 4, pi by 64 d raised to 4 minus small d raised to 4 into 2 by d into, take this denominator in numerator, 4 by pi, that means 4 by pi d square minus small d square. So that is it. So exx should be less than equal to, this is 8, and 8 is a 64. So this is pi by 8 d raised to 4 minus, this is 2 into 4 is 8, and 8 is a 64. Pi by 8 d raised to 4 minus small d raised to 4 divided by See, this pi also get cancelled, so no need to write here pi. Directly 1 by 8 into d. This d is remaining, and d square minus small d square, not 4. So this exx should be less than equal to. So write this d raised to 4 as like that. I will tell you why we have been write like that. This is 8 as it is, d square minus small d square. So this x should be less than equal to a square minus b square formula, a minus b into a plus b. So this is d square minus small d square into d square plus small d square divided by 8d d square minus small d square. So d square minus small d square get cancelled. So remaining is this. So this exx should be less than equal to that d square plus small d square divided by that 8d. So this is the load can be eccentric on any side of the geometrical center by the amount equal to d capital D square plus small d square upon 8d. So see, moment of inertia for that circular hollow circular section about I x axis and about y axis both are similar and area is also similar. So that's why now we are able to consider like that eccentricity from here to here is this exx, and exx distance is nothing but that capital D square plus small d square upon 8 into capital D, and this is also exx, and this is eyy, and exx and eyy both are similar. So that is the kernel of this section, core or kernel, this. So if we apply that load inside that kernel, so there will be no tension here, only compression will be here in that portion. But if you apply here in that portion all, but if you apply that load outside that kernel, then there will be chances to that tensile. So that is the meaning of that derivation. Eccentricity should be less than equal to capital D square plus small d square upon 8 into capital D. So okay, thank you very much. So now we will find eccentricity for hollow rectangular section. So this hollow rectangular section of outer width capital B and outer depth capital D and inner width is small b and depth is small d, and this is hollow rectangular section. So that means this inner portion is hollow, this portion. So how to find that eccentricity for that hollow rectangular section? So it eccentricity, that means that eccentricity that where that tensile stresses 0. So for that use our zero eccentricity equation. E should be less than equal to z by a. Now apply exx should be less than equal to zxx by a. So this exx less than equal to zxx is nothing but the moment of inertia about xx axis divided by y and a. So exx less than equal to ixx. So now this is ixx. So parallel side is this capital B. So ixx is capital B d cube by 12 minus small b d cube by 12. Okay, this is moment of inertia, and y is nothing but the distance from that x-axis, outer fiber up to outer fiber. So that means this is capital D by 2. And now find area. Area is area for that circular, sorry, for rectangular hollow section. BD minus small b into D. That is area. So rearrange it mathematically. Exx should be less than equal to 1 by 12 into bd cube minus small bt cube. Divided by d by 2. Okay, take this on numerator, d by 2, that means 2 by d, and this is bd minus, okay, take it as it is, bd minus small b into d. So this exx should be less than equal to this 6, 2 6 are 12. So this is b d cube minus small b d cube divided by 6d into bd minus small b into d. So check it. Yes, exx should be less than equal to capital B capital D cube minus small b small d cube 6d bd minus small b small d. So this is correct. And now calculate E for EYY also. EYY should be less than ZYY divided by area. So this EYY should be less than ZYY is moment of inertia about YY axis divided by Y distance and at A. So this EYY should be less than equal to, calculate moment of inertia about YY axis. So YY parallel side is D, so D as it is B cube by 12 minus small d B cube by 12, and Y is that distance from that YY axis, that means this distance, and C, this means outer directly, outer fiber distance, that means this is B by 2, capital B by 2. And into area is capital DB minus small db. So again rearrange it mathematically. Exx should be less than equal to db cube, so 1 by 12 take common, db cube minus small db cube, okay, into 2 by b db db. So this exx should be less than equal to 2 6 are 12. So this is like that, db cube minus small db cube divided by 6b db minus small d into small b. And see, we had make mistake here, that is EYY. So this is eccentricity about that yy. So db cube minus db cube upon 6b into db minus db. Yes. So now meaning of that is that eccentricity should be like that. So this is here exx, exx, exx. No, yes, exx, exx, and here eyy, eyy. So that means like that portion inside that there is no tensile stresses. So this is meaning of that. This portion is eyy and this portion is eyy, and this eyy exx values are nothing but that should be, see, exx should be less than equal to bd cube minus bd cube upon 6d bd minus bd, and that eyy should be less than that value. So that way, like, you would achieve that your zero tensile is zero tensile stress. Yes, within that region. If you go outside that region, that means somewhere here, then there will be tensile stress, but inside that region there these are only compressive stresses. Okay, thank you very much.